Okay, so welcome to another week of Intro CP. This is our second last week of presentations. Next week, we're covering dynamic programming. Then we break for Thanksgiving, and we then have a mini contest. But more details on that later. So yeah, please make sure you have the slides open, and then let's get started. Okay, yeah, just like before, feel free to discuss the problems on our Discord forum. It's open to anything related to the material or the contest, or basically anything, related to the previous presentations. We'll probably pause for another minute here. So if you have anything that you want to address, for example, if the slides could be more accommodating, if there's something that you feel should be addressed, please fill out this form. So we'll just wait for a minute so people have some time to fill that out. All right, I think we can get started. Okay, so the topic for this session is binary search. But before we get into it, let's just do a quick recap of last week's presentation by Tony. It was on sorting, and essentially what sorting is, it's just simply putting things in order. It's a really useful pre-computation, as we're going to see today, for binary search, and it leads to more efficient solutions. So yeah, as you saw, there are a lot of problems that we can expedite or make faster using sorting. And we're going to see binary search as one of those algorithms to do so. Okay, so what exactly is binary search? Well, in a single line, in the most simplest way, it's an efficient method to search through a list of values or solution. And we're going to see how this simple case allows us to abstract it to a greater class of problems, and we'll see exactly how powerful this can be. Okay, so for this presentation, we're going to first cover what do we mean by search, a real quick 5-minute intro of what we mean by search in computer science. Linear versus binary search. So we're going to look at a quick and easy solution to search known as linear search and see why binary search is better. We're going to do a simple case of binary search where we're looking for a specific number. And then we're going to abstract binary search to a whole class of problems to see exactly how efficient and how amazing it can be. Okay, so what do we mean by searching in CS? It's really basic. It's exactly what the name suggests. It's basically looking for a particular value in a list. So for example, say you have the list of available items or available sandwiches at BCAF. How do you find that one sandwich that you've been really craving for? So BCAF, for freshmen who have never been to UCLA so far, I'm sorry, it's basically one of the restaurants on the hill. And you have some really delicious sandwiches there. So, given a list of sandwiches, how can I find the one that I really want? So for example, suppose I have these list of sandwiches that go from turkey, chipotle barbecue, PB&J, chicken ranch, and vegan barbecue. How can I find that PB&J sandwich that I'm really craving for? Okay, so I guess one quick and easy solution is that you could just look at all the elements. So I could look at all the elements from turkey to chicken ranch to vegan barbecue and see if I find the sandwich that I'm looking for. But let's try to look at the time complexity of the solution. So in the worst case, I might have to end up looking at all the n sandwiches. So in the worst case, I would have a time complexity of O of n. But the whole point of this lecture or this presentation is, can we do better? And yes, of course. I mean, that's the whole point of binary search. But we're going to see that it's not so simple. And there's a little caveat that is sorting. So we're going to say yes and no. All right. So for binary search, we're going to actually first assume that the data is in sorted order. So for strings, sorted order simply means the dictionary or lexicographic order. For example, chipotle barbecue comes before PB&J because C is smaller than P in the dictionary. And similarly, PB&J comes before roasted salmon because P is smaller than R in dictionary order. So we'll first go through the general algorithm of binary search, and then we'll see why this works, and just analyze how this works and why this works. So bear with me while we go through the algorithm, and then we'll break it down. So the first thing I tell you is to look at the middle element. So what do we mean by middle? Well, this is simply the element roughly the element that is middle is the one that divides the list into two parts of equal size. So over here, roasted salmon would divide the list into two parts, one with chicken ranch to PB&J containing 3 elements, and then the Cuban to vegan barbecue. So roasted salmon is the middle element. We first look at the middle element and we compare it to the desired. So, I'm looking for PB&J. I see if PB&J is equal to roasted salmon. In this case, it's not, but it turns out that roasted salmon is in fact greater than PB&J. So what does this mean though? So at this stage, when we see that roasted salmon is greater than PB&J, since the list is sorted, we know that anything that comes after roasted salmon, for example, let me bring up my pointer. Anything that comes after roasted salmon, that is from the Cuban to vegan barbecue, will also be greater than PB&J because it's greater than roasted salmon. So you'd have PB&J is greater than roasted salmon, is greater than anything that is on the right of roasted salmon. But since we already know that it's going to be greater than PB&J, there's no reason to look for it. I mean, there's possibly no way I could have PB&J in the right half. So I can simply eliminate it. And the reason I can do this is because I know that the list is sorted. So if the list is sorted, I know that anything that comes after roasted salmon is going to be greater than or equal to roasted salmon. So there's no point looking at it for PB&J because I know PB&J is smaller. So we can simply just eliminate the right half in just one step without ever having to look at it in the search space. And now we just limit ourselves to 3 elements, which are the first 3 in this list from chicken ranch to PB&J. And I again repeat the process. I look at the middle element, which is chipotle barbecue. I see that chipotle barbecue is in fact smaller than PB&J. But again, just by the same logic, we know that anything that comes before chipotle barbecue will be smaller or equal to chipotle barbecue, which is smaller than PB&J, which means that chicken ranch is automatically smaller than PB&J, and there's no reason we have to look at it. So we can simply eliminate that half as well. And finally, once we eliminate these 2 elements, we're only going to be left with PB&J, and that is the element we're looking for in this case. So we'll return found, or we'll say that, okay, we have found that one sandwich that we've been really craving for. Great. So yeah, in just one check, we were able to eliminate checking half of the list, or the remaining half of the list. So let's try to, if that example wasn't super clear, let's look at a bigger example with 20 elements. We're going to look at 20 numbers that are in sorted order, and these 20 numbers range from 1 to 99. And we're going to maintain the start and the end of our list using these low and high pointers. So suppose we're looking for the number 14 in this huge list of numbers, or rather in this 20 list of numbers. And we repeat this, we do the same thing like we discussed before. We will first look at the middle element, which happens to be 51. We then compare 51 to the desired element. In this case, since 14 is smaller than 51, again, since the data is in sorted order, anything that comes after 51, that is 66, 69, 81, et cetera, will all be greater than 14 as well. So why bother looking at it? Because if there's an element that is greater than 51, it cannot be possibly equal to 14 because 51 is greater than 14. So we can simply eliminate the entire right half in one single check. So there's no point looking at any of these elements. We now constrain ourselves to the smaller list that goes from 1 to 45, and that is represented by the low and high pointer. And we look at the middle of this list, which happens to be 11. We then compare, just like before, we compare 11 to 14 and realize that 14 is in fact greater than 11. But what does this mean? Well, this means that any element that comes before 11 is also smaller than 14, or rather 14 is greater than that. So again, there's no point looking at it. So we can again eliminate that half, including the 11. We now constrain ourselves to these 4 elements, and then we calculate the middle. Now you know that even sized lists have 2 middles, but we're just going to look at the first middle from the left, which is the smaller middle in terms of index. So we look at 26, and we see that 26 in fact greater than 14. So just like before, we can ignore the right half. So we ignore 26, 44, and 45. And in this case, we're only left with one element, 14, where the low, middle, and high all coincide. In this case, we check that 14 is equal to 14, and we have found the element that we're looking for. So you might be wondering that what if the list does not contain the element? That works as well. For example, suppose this was a 13. In that case, when you're only left with one element and you compare the 13 and the 14, you realize that the 13 is smaller than 14, and you will end up advancing, as we'll see in a bit in the code, you'll end up advancing the low pointer, and that would basically mean that the low is greater than the high. So that would mean that you've exhausted your list and there are no more elements to check. Once you have this certain condition, you're safe to assume that you've not found the element, and you can simply have some sort of flag that tells you if you found it or not. So yeah. So it also works. So binary search also works if the element is not found in the list, and you can do code and you can branch accordingly. Okay. So how do we actually eliminate half the list every time and calculate the median repeatedly? Like you'd see before, every step we were actually having the list. For example, we got rid of this half in that smaller subarray, and then earlier we got rid of this list. How exactly do we do this? It's obviously super expensive to create a new list every time. So the idea is we maintain a low and high pointer, just like the previous example. And how do we update this low and high pointer? So in the previous example, we wanted to ignore the guess that we were looking for as well. So to eliminate the left half, we would simply increment the low pointer to middle plus 1. So middle was the current guess or the current element that we were looking at, and we increment low to mid plus 1. That is effectively eliminating the left half, since low, it maintains the start of the array. So you basically want to start at this new position. Similarly, to eliminate the right half, you would set high to mid minus 1, which essentially just ignores the right half, anything that was greater than mid minus 1 in index. And to calculate the median in the shortened list, so now that your list is shortened by low and high, you basically just compute the middle by taking the average of the two indices. Now, this always works for positive numbers when low and high are positive, such as the case in indices. But there's a slight modification that you'd want to make if you're working with negative numbers. But since we don't have any problems like that in the contest, I've chosen not to put it, but it's a really tiny change. Okay, so let's just walk through the code before we look at our first example and our first example problem. So the first thing you want to do, like we said, is sort the numbers, because the assumption of binary search is that you have some sort of intrinsic order or some sort of sorted order to the list. The next thing we do is we set the bounds. The first thing you want to know is identify what the smallest and the greatest solution can be. So in this case, since we're dealing with an array, the smallest index can be low, where the first element can be found, or the smallest element can be found. And we set high to the largest index, which is the size minus 1 of the array. That is basically the largest possible index. We also set up a flag, which is a Boolean flag that just represents whether we found an element or not. And we can branch based on this value later on after the binary search. Okay, so I'm going to skip that condition for the while loop for a second, but we'll circle back to it. And just like on the previous slide, we calculate the middle of the array by taking the average of the two indices. And we then check whether this middle element, referenced by num sub mid, is equal to the element that we're looking for, which I've labeled as des. And if that's the case, then that's great. You've found your element. So we set is found to true, and we break, because even if the list contains duplicates, that's okay as long as we found the first one, at least for this problem. So we end up breaking and look no further. Else if it's possible that the desired element that you're looking for is in fact greater than the middle element that you just saw. Well, in this case, you know that any element that came before the middle will also be smaller than desired. So why bother looking at it, and eliminate the left half by setting low to mid plus 1. Just opposite, contrastingly, if desired is less than the middle element, which is referenced by num sub mid, you know that any element that comes after the middle will also be greater. So why bother looking at it, and eliminate it again by setting high to mid minus 1. And finally, how do when do you stop? Basically, if you never found the element, there will come a point when you're looking at a single element. And if that element is greater or smaller, you will end up advancing low or high. And at this point, low would actually exceed high, or high would basically exceed low from the bottom. And this would mean that you've finished searching your entire list. Since start has exceeded the end, you don't have any more elements left in the list to check, and you can simply exit. And that is the code entirely. So I'll pause for like 30 seconds to enter, if you have any questions about the code or something I talked about before, yeah, feel free to unmute yourself or drop it in the chat. Just wait for 30 seconds. Okay. Great. So now that we looked at the code, let's try to analyze this a little better to see just how fast binary search is. I mean, it definitely seems faster, right? Because at every step, you're eliminating half the elements. And at linear search, when you're looking at one element, you're only eliminating one at a time. So yeah, we're going to analyze the time complexity in big O notation like we discussed in last week's presentation. So let's look at the worst case time. So in the worst case, we keep having the list until we're left with only one element, right? Like in the previous example, we kept having the list until we were only left with 14. And that was somewhat the worst case, I believe. So what you want to see is exactly how many times can we have this list of length n, because that is exactly what the operation is in binary search. You're always having this list. Great. So every time we have a list, we divide the length by 2. So, if you have a list of length n, when you divide it by 2, you get a list of length n over 2. When you divide that, you get a list of length n over 2 divided by 2, which is n over 4. So how many times can we do this? Well, if we have the list k times, the length of the list will be n over 2 to the k, just because, if you have n over 4, that'll be n over 2 squared. Then if you have n over 8, that's n over 2 cubed. So every time you have a list, you're dividing it by 2. So it just increases the power. And what you want to calculate is, in the worst case, when does the length reach 1? When we're left with only a single element. For example, in every one of our guesses, whenever we have the list, we never found the desired element. So we kept having it until we were left with only one element. So we're looking for that value of k such that n over 2 to the k is equal to 1. And if you guys remember your logarithms, that is exactly when k is equal to log base 2 of n. And if you haven't seen logarithms before, just think of this as the value. K is basically the value you need to raise 2 to get n. So 2 to the k is equal to n. And this is exactly what logarithms represent. So in binary search, every time we have a list, we perform a constant multiple of these k steps. These multiples being a constant number being, we first do a comparison, and then we increment the lower high pointer. So, or rather the index. So we always perform a constant number of these k steps, which basically means we can drop the constant, and the complexity is just O of log base 2 of n. And if that makes sense to you, it's still funny, just a function O of n versus O of log base 2 of n. What does this even mean? Like, why is log base 2 of n better than n? Well, the idea is that log base 2 of n is a slower growing function. So as n goes bigger and bigger, log base 2 of n does not grow as much as n. And to give you a better, more concrete idea, let's look at a database of 1 million entries that are in sorted order. Again, we assume sortedness because we assume a sorted order, but else binary search will not work. And in the worst case, linear search will end up looking through all 1 billion elements. For example, it's looking for the name Rohit, but it turns out that Rohit's the last element in the last record in the database. So it'll end up taking 1 billion searches, which is too slow. But if you do binary search, if you do log base 2 of 1 billion, that is in fact only 30. So you will do about approximately only 30 steps. So you can already see how slow growing the function log base 2 is. Like for a billion entries, O of n, or rather a linear function, is about 1 billion entries, but a log base 2 is only 30 entries. You will only have to end up checking 30 entries before you get the one you're looking for. So you can see how efficient that is. Awesome. But I guess we should address the issue of sorting. So, we said that in the beginning, we need to sort the array, but it turns out that sorting is more expensive than linear search. So if you have to sort the data in the beginning, you might as well do linear search, right? And normally that is true if the data is unsorted and all you're doing is a single search. But often in competitive programming, what you're doing are multiple searches. You're doing searches sometimes, to the order of the number of elements. So you'd basically be doing a linear search O of n times, or like maybe for every element, for example. And you'll see some problems where this happens. And that would lead to an O of n squared algorithm. You're doing an O of n linear search O of n times, which is an O of n squared time complexity. But in binary search, for every O of n, for every of those O of n times, you will be doing a log n search, or log base 2n search, which basically leads us to an O of n log n algorithm. And if you do not know, I mean, we could probably talk about this after the presentation. O of n log n is actually much better than O of n squared. And since sorting is also O of n log n, sorting does not add any complexity to O of n log n, so it ends up being more efficient. If you're going to sort and do binary search multiple times, it's much better than linear searching. Yeah, so if you have any questions about why n log n is better than n squared, you can ask us after the presentation. But the idea is, again, the same, that you compare the n and n, those are the same. But then, like I said before, log n is a lot more efficient than n squared. It's a lot more slow growing. So n log n as a whole grows much slower than n squared. Okay, yeah, but binary search goes even further than that. Like in the previous example, we were just searching a list of predefined values. But binary search, you can search over anything that has an intrinsic order, which can be the integers, real numbers, and there are more examples that we're going to discuss later. But you don't actually have to have a concrete list of numbers. And you're going to see in the next example problem A, where this is the case. So yeah, and we will abstract binary search to a bigger class of problems very soon after example A. Okay, so that segues us into our problem A, which is called guess. And it's a very interesting problem. It's an easy problem, but it's interesting because you probably haven't seen this kind of problem before. So I'm just going to quickly go over why this problem is kind of unique, and then I'll flip back to the slide for the links. So yeah, so this is something called, I'll give you a second to open it. It's called guess the number, and this link should take you to the examples. But what makes this problem unique is that, or something that you probably haven't seen before, is that it's an interactive problem, which means that the program just doesn't have some test cases, but it actually responds to your output. So basically, it's like talking to another human being or talking to the computer in this case, or in this case, Caddis. So you basically, whenever you print something out to standard out, Caddis would actually respond based on your output and give you some new information. We formally call this output a query, and every time we make a query, Caddis gives us new information about based on our as our response based on our guess or based on our query. And every time it gives us a response, we learn we hopefully learn something new and do something in our algorithm. So another thing to note is that there's no list in this problem, but we'll still search over the numbers from 1 to 1,000. Okay, great. The sample template here should be very helpful, and let's give you 5 minutes to solve this problem. I really hope you can code it out because I want to make sure you can code out binary search at least once before we get into example B. Let's get started. All right, so let's skip over the explanation. It's an interactive problem like we discussed before, and let's jump right into the solution. So checking every number from 1 to 1,000 will not work because the problem specifically says that we only have 10 guesses. So if the number was 11 and you check 1 to 10, you're out of your 10 guesses already. And checking these numbers in order from 1 to 1,000 is exactly what linear search is. So let's instead try binary searching over the space of the possible solutions. And what I mean by this is that we're no longer storing these solutions in an array from 1 to 1,000, but we're actually just going to think of them abstractly. Like we're starting from 1 and we're starting from 1,000. And we're going to see why this works in a little bit. But suppose Caddis has this hidden test case of 278. So it's basically, it wants us to guess 278. The first thing we do is identify our lowest and highest possible solution, which is 1 in 1,000, just like we did with low and high in the previous slides. And we repeat the same process binary search. So you compute the middle element, which is 1 plus 1,000 divided by 2. Since you round it down, that ends up being 500. You guess 500. Now, when you see out 500 to Caddis, Caddis is actually going to respond with lower, because in this case, 278 is in fact smaller than 500. So after our first guess, we actually know that our element is smaller than 500. But then again, just like the previous example, since 1 to 1,000 have the same order that 1 is less than 2 is less than 3 is less than 1,000, so on and 1,000, we know that we can eliminate every element that is greater than or equal to 500. Because 278 is in fact smaller than 500. So it's smaller than 501, it's smaller than 503, and it's smaller than 1,000, etc. So, since we want to eliminate all those elements greater than 500, just set high to 499. That means we're not going to bother looking at any element greater than 499. And repeat the same process. So 1 plus 499 is 500, divided by 2 is 250. You compare 250 to 278, and in this case, since 278 is greater than 250, Caddis would end up reporting higher. And now that we know that 278 is higher than 250, we know that it cannot be possibly smaller than 250, right? So we can eliminate any element that is between 1 and 250, which is essentially setting low to 251. And notice how just in 2 guesses, we went from 1 to 1,000 to just 259 to 499. We've halved our data twice already in just 2 guesses. So again, we look at 251 and 499. Again, we repeat the same process and we make a new guess, which is the middle of 251 and 499. Again, the middle is just the average. So we make the guess 375, which is our guess number 3. And again, we ask Caddis what it thinks about 375, and it says that it's in fact the number that it wants is smaller than 375. So in this case, we now know that any element that is 375 or greater cannot possibly be the element Caddis is thinking about. So we limit ourselves again to any element that is smaller than 375 by setting high to 374. Finally, we repeat this again. We see that the average of the middle element between 251 and 374 is 307. We compare 307 to what Caddis had in mind, and Caddis would end up reporting lower. Again, these are responses of Caddis. And I think there's something in the chat. Oh, never mind. So Caddis would end up reporting lower since 278 is smaller than 307. In this case, again, we now learn more information that any element that is 307 or greater, it cannot possibly be what Caddis is thinking about. So we set high to 306. And now we constrain ourselves to just about 49 plus 6 elements, about 55 elements. That's it. We went from 1,000 to 55 in just 4 guesses. And yeah, and then we repeat the process one last time to see, and the average between 251 and 306, the middle element is 278. And in this case, since 278 is equal to 278, Caddis would end up reporting correct, and we can exit our code. Look at that. It only took us 5 guesses, and Caddis actually gave us 10. In fact, I think in the worst case, you would end up taking 10, but for this example, you ended up taking 5. Okay, so here's the code. It's very similar to the previous one, but the only difference is that this interactive section where we print out our guess and we expect a response from Caddis. And based on what this response is, we either branch if it's higher or if it's lower. And finally, if it's correct, then we just exit our while loop. But yeah, it's the same idea like before. Mid plus 1. So we just relabel it to guess, and high is equal to mid minus 1. And we relabel that to guess. Great. I hope that was easy to understand. I'm going to move on. And if you have any questions, when we pause for the next problem, maybe you can ask me then. Okay. So the one thing to note is that in example A, there was no such actual list, right? We never stored the numbers between 1 and 1,000. And in fact, there was also no sorting because there were no such numbers that we had to sort. And the numbers, in fact, the numbers from 1 to 1,000 are technically already in some order. And this sorted order is basically just the numbers, just the ordering of the integers that go from 1, 2, 3, 500, 501, so on to 1,000. And we know this ordering is basically just the inequality of less than. And this actually leads us to an important property that we need to eliminate half the list. And that is the following. If something is true for an element, it is also either true for every element before or every element after it. For example, when we looked at 500 and we compared 278 to 500, since 500 is greater than 278, it is also true that any element after 500 is also greater than 278. So over here, our something is an inequality between 500 and 278, but between the element that we guessed and 278. And if it's true for our guess, it ends up being true for any element after the guess as well, in terms of in this order. So this order is just the order of the integers. And that allowed us to eliminate all those elements because we were looking for, in this case, we were looking exactly for 278. So we could eliminate all those elements for which it was unequal. And to understand this a little better, to understand how this ordering works and how this is true for every element or before or every element after, we will look at a slightly more involved example where we're not looking for strict inequality anymore, but we're actually looking at an inequality. We're looking for the smallest element greater than or equal to 200. So now this list may or may not contain 200, but we're looking for the next best thing. We're looking for the element that is the smallest element that is greater than it. So what's the next thing that you can do if you cannot do 200? For example, in this case, the answer will be 227. That 227 is the first number after 200 that is greater, after 200 basically. And let's again assume that the numbers that I have are in sorted order. You could do this just by running sort, but let's just assume I have it sorted for this example. And yeah, just like I said, we're not looking for equality any longer. And before we just jump into the code, I believe just looking at the code is also intuitive for this problem. We're actually going to formalize this a little bit so that we can abstract binary search to a bigger class of problems that are more involved, what we're going to call predicates. So let's first define this function that we call a predicate. A predicate is basically simply a function that returns either true or false based on some condition. And we're going to define the condition as follows. F of x is true for some value x if x is greater than or equal to 200. Well, what does this mean? So if you have any value and you pass it to f, it's just simply going to return true if it's greater than 200. So in this case, if you run f of x and we map out and we just write out the table for all the values we have in our list from 1 to 921, we're going to realize that all these elements from 1 to 199 are false because they're all smaller than 200. And all these elements after 227 to 921 are going to return true because all of these elements are greater than or equal to 200. In this case, strictly greater. So yeah, you're going to see that these are all false and these are all true. So yeah, we're going to see how we're going to use this function in our binary search. So our goal basically is now to find the smallest value of x for which f of x is true from the left. Because that would be the first time when we switched from false to true, that would be the first time we found an element that is greater than 200. And that is exactly what we want. We want the smallest element. So we're basically looking for that smallest value of x for which f of x is true. And let's look at some sample examples. For example, we were doing our binary search, having those elements like we did before, and we somehow ended up at 173. So we first checked this function on 173. Since f of 173 is false, we can actually safely eliminate 1, 92, and 173 because we have all of them to be false as well. And this follows because every element that is smaller than 173 is also smaller than 200. So all of these elements cannot possibly be the number we're looking for. But let's think of it in this way though, that the function all returns false on these values as well, and simply just because the predicate is an inequality with 200. And so yeah, that would basically mean we can simply eliminate 1 to 173. Let's do the same thing, but now let's look at some element 420 that's in fact greater than 200. Now, since f of 420 is true, we can safely eliminate 620 to 740, 620, 749, and 921. Why? Well, because we're looking for the smallest such number, and we've already found our candidate solution. It could be 420. So why? And since 420 is smaller than any element that comes after it, we don't have to bother looking at those elements because we're looking for the smallest possible one, and we already have 420 in the hand. So why look at 620? And what's different here is that in the previous example, when we looked for equality, since 420 was, say, for example, not equal to 200, we would end up eliminating 420 as well. But in this case, we're looking for the smallest number. So we need to ensure it's also possible that there's no number between 200 and 420 in this list. So you cannot eliminate 420 at this point. Yeah, so you can eliminate all those three elements. And the important condition that we're going to use here, and the important condition that we basically use here, that if it was false for 173, it was false for every number smaller than it. And if it is true for 420, it was true for every number greater than it. And this is, and if you have this sort of predicate that satisfies this condition, and we're going to get more formally into that condition, f of x is basically going to look like a bunch of falses followed by a bunch of trues. That is because if there was a true somewhere in between these falses, then this condition will no longer be true. For example, if you look at f of 199, which happened to be the largest false, this condition guarantees that anything that is smaller than 199 will also be false, will also return false when evaluated with f. And therefore we cannot have this true value somewhere in between. Similarly, for true, we cannot have any false value in between this sequence of truths, because then you would violate this condition here, that it's true for all numbers greater. So yeah, so you'd see this, you basically want to find this turning point when this false changed to true for the first time, to find the smallest number on which it returns true. And we can do that using binary search. So yeah, in fact, you can prove that. So we're not going to go into the proof, but you can basically prove that if you have any predicate P that produces this sequence of falses followed by trues, or vice versa, trues followed by falses, then you can always find the smallest or largest x such that P of x is true using binary search. So in this case, P of x is true would be, and the smallest x would be 227. We're looking for the smallest value greater than 200. We don't really prove this, but the intuition should be clear once we look at the binary search code in a bit. Okay, so let's jump right into the code. So like I said, we define our predicate here. That is a very simple predicate. In fact, you probably never want to make this into its own function, but it's helpful for understanding the abstraction. Basically, the predicate checks if some value that we provided is greater than or equal to the bound, in which case it's 200. And that is exactly what it's a very simple function, just checks if something is greater than or equal to a bound. We then, like before, sort the numbers because we cannot do binary search if the numbers are not sorted. We need to rely on that guarantee that these numbers have some sort of order. And we then set up our bounds. The lowest index is 0, and the highest index is the size -1. Just like before, we exit when low is greater than high. And like Jacob said, this can also be low is less than high, but then you'll have to change your implementation a little bit. And because, yeah, so once you exit, you'll have to check if low, so you basically need to probably, in this case, only check the low. But if you have more questions on that, we can do it after the presentation. And yeah, now if f on the guess, which is num submit, which is referenced by num submit, returns false, well, this is the case of like checking 173. When we check 173 and we know the function's false, we know that's going to be false for any value that came before it. And to eliminate any value that came before it, we can simply do what we did before, update low to mid +1. And this is essentially moving the start of our new subarray to eliminate all those elements that came before mid. And else if the function returns true, for example, in the case of when we're looking at the value 420 or the value 620, for example, we would end up setting high to mid. And the difference again here is that we don't set high to mid -1 because we don't want to ignore the first value for which it is true, because that could in fact be the solution that we're looking for. Finally, when we update a value, and this is where the implementation would differ if you have low is less than high, finally, we check if low is equal to high. And we only do this, this is basically the case of one element. And we only do this in the case when we update high, because this is the case when the function is true. Since we're looking for the smallest true, binary search would basically converge over to that one element for which this function was true, since we always kept it included by setting high is equal to mid. And at that point, we simply print it out in this case, and we break. You could do many things. You could set a flag to say is found is equal to true, depending on your code. In this case, I just wanted to print it out. So I just printed it out over here. And that's the entire code. Again, I'll pause for 30 seconds to entertain any questions. I hope this was easy to understand. Is there something in the chat? Yeah. Make sure you understand what predicate means. It's simply a function that returns true or false. But if you have some question on the predicate that I just defined, feel free to unmute yourself or drop it in the chat. Okay, so you might be wondering, why did we go about this roundabout way? Or maybe it's not roundabout, but why did we go about this formal way of showing some sort of function and evaluating some sort of function? And the reason I did it this way is because this abstraction is really useful for once, but often in competitive programming, we're looking for some sort of maximum or minimum value for which something is optimal. So, basically, in many times, you're not looking for a specific value. You're not searching for an exact value, but you're searching for some assignment which minimizes some cost or maximizes some utility. So we're looking for some assignment x such that f of x is less than y. And this function, this predicate f, can actually be quite involved. It doesn't have to be an O of one predicate that is simply like a check of whether something is greater than a bound, but it could be something like an O of n predicate where you're checking where you actually iterate through an entire array of something and check if this assignment satisfies some condition. And actually, no, I'm not going to give that spoiler. Okay, great. So that abstraction is useful for that case. So we're basically going to break modeling a problem as binary search into two halves. First, identify the solution space, and second, design the predicate. Basically, when you're designing a problem for binary search, I want you to think of these two things, and basically, just think of these two things, which will help you really code out the solution. So the first thing is identify the solution space. Identify what you're binary searching over. For example, in the previous examples, we were binary searching over the indices, and we were looking for the element that satisfied the particular function constraint. And you want to determine the smallest possible candidate solution and the largest possible candidate solution, which will help you set your low and high bounds. Normally, it's sometimes very extremely clear from the problem. Sometimes you can just set it to any arbitrary low or high value, but in some cases you can't. For example, in the indices of an array, you cannot exceed from the bottom 0, and you cannot exceed from the top the size of the array -1. So it's very likely clear from the problem. And sometimes you can determine what the largest possible solution is based on the constraints of the problem given in the input section of the problem. Okay, yeah, so you basically want to find the minimum x and the maximum x that you want to check with the predicate. And the second solution is designing that nice predicate. By nice, I mean that it satisfies this condition I'm going to get into, and that it's also efficiently calculable. And by efficiently calculable, I do not mean that it has to be O of 1. It can also be O of n or a little more involved. But basically, this predicate, like before, checks an assignment x. For example, in the previous one, it checked if x is greater than or equal to bound. And basically, it checks for some maximum or minimum condition. And the important property that it needs to satisfy, however, is that if the predicate is true for some x, it is also true for all the y greater than x. And if the predicate is false for some x, it should be false for all the y smaller than x. Just like in the case of the elements from 1 to 1921, if it's false for, say, 173, it's false for all the elements smaller than 173. And over there, we binary searched over the indices. So x and y over here would be indices, but our predicate would be checking A sub I, where A is the array. And yes, this predicate can be flipped. So, you could have that it's false for all x. So it should be false for all y greater than x, and true for x. So it should be true for all y smaller than x. So the true and false can be switched. But you basically, what I'm trying to tell you is that you need a bunch of falses followed by a bunch of trues, or vice versa. You can't have a false embedded in the true, or a true embedded in the false. And just opening, okay. So yeah, and this is actually the trickiest part in binary search. In the previous example, it was kind of easy. We just checked if it's greater than or equal to some bound. But this, like I said before, and you're going to see, it can be a little more involved with like maybe an O of n predicate. So you need to basically determine how do you verify or how do you validate whether your guess is a valid solution. And then you reduce your search space to find the smallest solution or the largest solution. Okay, that naturally segues into our next problem example B that is going to be covered by Rishi. But I basically want you to look at, I want you to identify, number one and number two, identify the solution space and identify that nice predicate. So I'll let Rishi take over now.
Cool. So let's go over the solution for the H-index problem. So first, really quickly, let's talk about just sample input 1 and 2 and how you get the sample outputs. And so essentially with sample input 1, you have the input 7, 1, 2, 1, 5. And so an H-index of 2 means that you have at least 2 papers with 2 citations. So in this case, we actually have 3. We have the 7, the 2, and the 5. Each of them has 2 citations, which means we do have at least 2 papers. So an H-index of 2 is valid, but an H-index of 3 would mean that we have 3 papers with 3 citations, and we only have 2. We only have the 7 and the 5 because the 2 is less than 3. So we don't actually have 3 papers with 3 citations. So because of that, we find that the largest H-index that's valid is 2. And so that's why the sample output 1 is 2. And then in the second sample input, we have, instead of a 2, we have a 3 here. And so that means that now we actually do have 3 papers with 3 citations, which would be the 7, the 3, and the 5. So that's why the second sample input is a 3. And so let's talk about how we would go about doing this problem. We are going to use binary search, of course, but more specifically, we're going to binary search on the value of the H-index. So what that means is that the solution space, which is essentially all the possible outputs that could be given by the program, is what we're going to binary search on. And so if you think about the worst case scenario, we want to think about what the possible H indices are. So this is like, what are the possible outputs for the program? And in the worst case, the lowest possible H index is 0. So this is the lower bound on the H index, and it's going to be the lower bound on binary search. And the reason for a lower bound of 0 is that in the case that each paper given in the input has no citations, then even an H index of 1 wouldn't work because there's not a single paper that has even a single citation. So the lowest possible H index is 0. And then on the other hand, the best case is an H index of n. And the reason for that is because we need to have an H index be valid, then you need to have n citations on n papers. And since we only have n papers, an H index of n plus 1 is never going to be valid because we don't have n plus 1 papers. So because of that, we sort of end up with a solution space that looks like this. So we have 0, 1, 2, and so on and so forth, and then all the way up to n. And then the second part of the solution is the predicate. And the predicate in this case is, it's a longer predicate. It takes order of n time, as it turns out. But the idea is pretty much the same, which is checking the validity of a specific element of the solution space. So specifically, we're trying to check, given a specific H index, is that a valid H index? So looking at sample input 1 as an example, we can check is H equals 2 valid, for example. So this is an H index of 2 okay? And so how would we do this? We would sort of have to go through all the numbers because we don't really know anything beforehand about the citations. So we would have to go through all of them. And the goal is to see, do we have 2 papers with at least 2 citations? So what we would have to do for that is we'd have to go through the whole array and check which ones have at least 2 citations. And what we'd find is that we have a 7, we have a 2, and we have a 5. And all 3 of these have greater than or equal to 2 citations. And because that's at least 2 papers, that means that yes, H equals 2 is valid. And another example is H equals 3 valid. And so once again, we have to go through the entire array because we don't have any like prior knowledge of the array elements. So we go through it. 7 is greater than or equal to 3. 1 is not, 2 is not, 1 is not, and 5 is. So overall, we have 2 papers that have at least 3 citations, which means that H equals 3 is not valid because we have less than 3 papers that have 3 citations. And so yeah, that sort of can be generalized so that given any H, to check if it's valid, you have to loop through the entire array of citations, and that's the sample input. And then you want to count the number of papers with at least H citations. So for each element in the array, you check is the number of citations greater than or equal to H, and then if it is, then you sort of increment a count and you keep track of a count. And then if that count at the end of iterating through the array was greater than or equal to h, then that means that the h index is valid. So looking at that in code, it sort of looks like this. You start with initializing a count variable, and then you iterate through the array. Each iteration, you check if that specific element of the array is greater than or equal to h, then you increment count. And then once you're done with your iterations, then you can check if your overall count was greater than or equal to h to see if that h index is valid. And then finally, we can put it all together. So we had our solution space. This is the solution space for the sample input where n equals 5. So we have 0, 1, 2, 3, 4, 5. And then our sample input itself is 7, 1, 2, 1, 5. And so we're going to binary search over the solution space, which is all the possible h indices. And binary search is order of log n, so that's the time complexity there. And then, so yeah, so when we binary search, we first find the middle element. In this case, it's the 2. And from there, for each guess, starting with a guess of 2 as your mid, you want to check the predicate. And the predicate requires going through the entire array. So that's an order of n linear scan. And yeah, so first, for example, here we check, is an h index of 2 valid? And as before, we have 7, 2, and 5. So it is a valid h index. And therefore, because the goal is to find the largest possible h index, we know that 2 is a valid one. So 0 and 1, even though they're also valid, they don't really matter anymore because we're trying to find the largest one. And if 2 is already an h index, then something less than 2 is not going to be the largest one because 2 is already larger. So because of that, we can eliminate 0 and 1 immediately once we find that 2 is valid. So yeah, if your guess is valid, then you eliminate the left half. So all the elements less than mid. And then after that, we can continue going on with binary search. The next step, we find the middle again. This time it's index 3, so element 3. And now we once again check the predicate. And this is again order of n. But this time 3 is not a valid h index. So we can actually realize that 3 can be crossed out. But more specifically, if a guess isn't valid, then the entire right half can be eliminated. And the reason for that is that firstly, we know 3 is invalid, but then that means that there aren't 3 elements that have a number, like a citation count more than or equal to 3, which means that there's also not 4 elements that have a citation count more than or equal to 4, because 4 is greater than 3. So if there's not 3 that are greater than 3, then there's not 4 that are greater than 4. So that means we can eliminate 4 and 5 and so on all the way up to the end. So if a guess is invalid, then you eliminate the right half. If a guess is valid, then you eliminate the left half. And so yeah, so that sort of translates to code. It's pretty similar to the code that Rohit showed for his abstracting binary search example, but at the beginning, you set your low and your high to be 0 and n, which are the bounds of the solution space. Then you iterate in a pretty standard way for binary search. You calculate the mid. And this is the actual implementation of the predicate. So this is the linear scan where you count the number of citations that meet the requirement. And then this is, for example, if h index is valid, then you eliminate the left half. And then conversely, you can eliminate the right half if it's not valid. And then, so yeah, finally putting that together, that gives you the code for this problem. And so yeah, that's the solution for problem B. Are there any questions before I move on?
So, may I ask?
Yeah, go ahead.
So for 0, if there's all zeros, that means the program should just return 0, right?
Yeah.
Okay. I'm sorry. I wasn't really paying attention. I was just looking at my program. So I bet yours probably points for 0.
Yeah. So if we look at the 0 case specifically, in that case, then count is never going to be greater than or equal to mid because count's always going to be 0. So I guess like it's going to keep on going until you exit out of the loop, and ultimately h index won't be changed. So h index will stay at 0, and then after the binary search loop is ended, you're just going to print out h index, and since it started at 0, you're going to print out 0 in that case. Cool. So yeah, that's the end of the slides. we have our feedback form as usual. It's tinyurl.com/introcp5feedback. So I'll give you guys maybe a minute or two to fill that out, and then we'll start the contest. And yeah, we'd appreciate any feedback, and specifically, like, if you guys like the breakout room thing for the problems, then let us know, or else if you didn't like it. Okay, cool. Hope you guys had a chance to fill that out. So yeah, here's the link to the contest. And yeah, I think we're going to open breakout rooms as usual per problem. And yeah, good luck.